Section 1. The Greatest Mystery. Why are we here? The universe is a vast and mysterious place. It is filled with stars, planets, and galaxies beyond our comprehension. But there is a fundamental question that haunts cosmologists. Why does the universe exist at all? The laws of physics suggest that matter and antimatter, when they meet, should annihilate each other in a burst of pure energy. Think about it. Every particle, every atom in your body, should have an antimatter counterpart somewhere in the universe. When they meet, poof, nothingness. Yet, here we are. We see a universe teeming with stars, galaxies, and life itself. This glaring discrepancy, this cosmic paradox, is one of the most profound mysteries in science. It suggests that there's something fundamental we don't understand about the universe's origins. Perhaps a subtle imbalance, a cosmic quirk, tipped the scales in favor of matter. Or maybe there are hidden symmetries, unknown forces at play that we're only beginning to glimpse. This is the ultimate cosmic detective story. We are searching for clues, piecing together the evidence to understand why the universe didn't simply annihilate itself into oblivion. And the answer, my friends, may hold the key to understanding our very existence. Section 2. Cosmic chess match. Matter versus antimatter. Let's delve into this cosmic chess match between matter and antimatter. Imagine the Big Bang, the moment of creation, an unimaginable explosion of energy, birthing a universe of particles. For every particle of matter created, an equal and opposite particle of antimatter should have emerged, like two sides of a coin, inseparable and destined to collide. But something extraordinary happened in those first fleeting moments of the universe. A slight imbalance, a tiny asymmetry, tipped the scales in favor of matter. For every billion particles of antimatter, there were perhaps 1,000,001,000 particles of matter. This seemingly insignificant difference had profound consequences. As the universe cooled and expanded, matter and antimatter engaged in a cosmic dance of destruction. Particle met antiparticle, annihilating each other in a blaze of energy. But that tiny surplus of matter, that one extra particle in 1,000,000,000, survived the cosmic carnage. That's us. We are the descendants of that victorious matter, the remnants of a cosmic battle royale. But the question remains, what caused that initial imbalance? What tipped the scales in favor of existence? To unravel this mystery, we must delve deeper into the subatomic realm, where particles dance to the tune of quantum physics. Section 3. Echoes of the Big Bang, Unveiling the Early Universe. To understand the matter-antimatter asymmetry, we need to rewind the cosmic clock, back to the earliest moments after the Big Bang. Fortunately, we have a remarkable tool at our disposal, the Large Hadron Collider, LHC, at CERN. This incredible machine smashes protons together at nearly the speed of light, recreating the extreme conditions of the early universe. Think of it as a time machine, allowing us to glimpse the universe as it was just fractions of a second after the Big Bang. By smashing these particles together, we create showers of new particles, some of which existed only in those first fleeting moments. Among them are antiparticles, the mirror images of ordinary matter. Studying these antiparticles allows us to probe the fundamental symmetries of nature. We can compare the properties of antimatter to their matter counterparts, looking for any subtle differences that might explain the cosmic imbalance. And the LHC has already yielded some tantalizing clues. For example, experiments at the LHC have shown that certain particles, called B mesons, decay slightly differently than their antimatter counterparts. This subtle asymmetry, known as CP violation, suggests that the laws of physics might not be perfectly symmetrical between matter and antimaterial. Section 4. The elusive asymmetry. Where did all the antimatter go? The discovery of CP violation was a major breakthrough, but it's not enough to explain the observed matter-antimatter asymmetry in the universe. The amount of CP violation observed in particle physics experiments is simply too small to account for the vast amount of matter we see around us. So, where did all the antimatter go? That's the million-dollar question, or perhaps the billion-dollar question, given the cost of these experiments. Some physicists believe that the answer might lie in the behavior of neutrinos, those ghostly particles that interact very weakly with matter. Neutrinos come in 3 flavors: electron, muon, and tau. And it turns out that neutrinos can oscillate between these flavors as they travel through space. Some physicists have proposed that there might be a fourth, hypothetical type of neutrino called a sterile neutrino. If sterile neutrinos exist and interact with ordinary matter in a specific way, they could have tipped the scales in favor of matter in the early universe. This is just one of many intriguing possibilities being explored by physicists around the world. Section 5. The Base Experiment, Probing the Antiproton's Secrets. To further unravel the mysteries of antimatter, scientists have devised ingenious experiments to study its properties with incredible precision. One such experiment is the baryon-antibaryon symmetry experiment, or BASE, located at CERN. BASE focuses on antiprotons, the antimatter counterparts of protons. Protons, as you know, are those positively charged particles that reside in the nucleus of every atom. Antiprotons, on the other hand, have the same mass as protons but carry a negative charge. The BASE experiment is designed to measure the magnetic moment of antiprotons with unprecedented accuracy. The magnetic moment is a fundamental property of particles that describes their behavior in a magnetic field. Think of it as a tiny bar magnet embedded within the particle. By comparing the magnetic moment of antiprotons to that of protons, scientists hope to uncover any subtle differences that might hint at new physics beyond our current understanding. And the results, my friends, are nothing short of astonishing. Section 6. A magnetic surprise, antimatter's unexpected behavior. The BASE experiment has been pushing the limits of precision in measuring the antiproton's magnetic moment. And in 2017, they announced a groundbreaking result. The magnetic moment of the antiproton is identical to that of the proton to within 1 part in 10 trillion. This extraordinary precision is like measuring the distance from the Earth to the Moon to within the width of a human hair. The fact that the magnetic moments of protons and antiprotons are so precisely matched is both remarkable and puzzling. You see, according to our current understanding of particle physics, there's no reason why these magnetic moments should be exactly the same. In fact, some theories that go beyond the standard model of particle physics predict a slight difference. This unexpected result has profound implications. It suggests that our current theories might be incomplete, and that there might be new particles or forces at play that we haven't yet discovered. It's like finding a missing piece of a jigsaw puzzle, one that could unlock a deeper understanding of the universe. Section 7. Implications for the cosmos, rethinking fundamental physics. The implications of these findings extend far beyond the realm of particle physics. They have the potential to revolutionize our understanding of the cosmos and our place within it. For example, the matter-antimatter asymmetry has profound implications for cosmology. If matter and antimatter had truly existed in equal amounts in the early universe, they would have annihilated each other completely, leaving behind nothing but a sea of radiation. There would be no stars, no planets, and no life as we know it. The fact that we observe a universe dominated by matter suggests that there must have been some asymmetry, some violation of fundamental symmetries that tipped the scales. And understanding this asymmetry is crucial for understanding the evolution of the universe as a whole. Furthermore, the search for antimatter has implications for our understanding of gravity. According to Einstein's theory of general relativity, gravity is a universal force that affects both matter and antimatter equally. Section 8. The Quest for Answers. Unveiling the Universe's Secrets. The quest to understand antimatter is a testament to the power of human curiosity and our relentless pursuit of knowledge. It's a journey that has taken us from the smallest subatomic particles to the largest scales of the cosmos. The mysteries of antimatter are a constant reminder that our understanding of the universe is far from complete. Every discovery, every breakthrough seems to raise more questions than answers. But that's the beauty of science. It's a never-ending journey of exploration, a constant striving to push the boundaries of human knowledge. And the more we learn, the more we realize how much more there is to discover. The universe is full of surprises, and the answers we seek are often hidden in the most unexpected places. So let us continue to explore, to question, and to marvel at the wonders of the cosmos. For in the words of the great Carl Sagan, somewhere, something incredible is waiting to be known. Section 9. The Future of Antimatter Research. Unraveling the Cosmic Puzzle. The future of antimatter research is bright with promise. New experiments are being planned, and new technologies are being developed that will allow us to study antimatter with even greater precision and detail. One exciting avenue of research is the development of antimatter traps. These devices use magnetic and electric fields to confine antimatter particles, preventing them from annihilating with ordinary matter. By trapping antimatter, scientists can study its properties for extended periods, allowing for more precise measurements. Another promising area of research is the study of antimatter gravity. As I mentioned earlier, Einstein's theory of general relativity predicts that antimatter should fall under the influence of gravity, just like ordinary matter. However, this prediction has never been directly tested. Several experiments are currently underway that aim to measure the gravitational interaction of antimatter. The results of these experiments could have profound implications for our understanding of gravity and the nature of the universe. Section 10. Conclusion. A universe of possibilities. The study of antimatter is a journey into the heart of the universe's greatest mysteries. It's a quest to understand why we exist, why the universe is filled with matter and not antimatter, and what secrets the cosmos still holds. The discoveries made in this field have revolutionized our understanding of particle physics, cosmology, and the fundamental laws of nature. From the early experiments that first hinted at the existence of antimatter to the cutting-edge research being conducted at CERN and other laboratories around the world, the pursuit of antimatter has been a triumph of human ingenuity and collaboration. And as we continue to explore this fascinating realm, we can be sure that even more astonishing discoveries await us. The universe is full of surprises, and the answers we seek may lie just beyond our current understanding. So let us embrace the unknown, celebrate the mysteries, and continue to explore the infinite possibilities of the cosmos. For in the words of the great Richard Feynman, there is plenty of room at the bottom.